Have you ever felt that? Yeah, that feeling you're just swimming in data, spreadsheets here, customer info there, maybe inventory reports somewhere else, and say, you've got so much information, but pulling it together for one clear picture to make those big decisions, yeah, often feels impossible. No single source of truth. Well, today we're diving deep into the solution for that exact problem, the Enterprise Data Warehouse, or EDW. We're going to unpack what these things really are, why they're basically the brains behind smart business decisions today, how they've changed like dramatically, and the tools and strategies you need to actually use them well. Our mission really is to cut through all the jargon and give you the solid foundation you need to understand how businesses turn all that messy, scattered data into, well, into insight. A single powerful view. Let's get into it.
Yeah, it's fascinating because an EDW, it really is that central hub. It's not just, another database somewhere. It's specifically built, engineered for complex analysis and reporting. It pulls data from, well, everywhere, CRM, sales systems, ERP, you name it. And its whole purpose, fundamentally, is creating that single source of truth. Breaking down the walls between different data sources so you get a complete long-term view of the business. That kind of view lets companies go way beyond just simple reports. They can find hidden trends, do much deeper analysis, even build predictive models.
That single source of truth idea is incredibly powerful. But I guess for someone new to this, maybe you're thinking, why can't I just run my big analysis reports on my normal systems, the ones we use every day? Why build this whole separate thing?
That's maybe the most critical reason for a data warehouse. It's this fundamental split between OLP, online analytical processing, and OLTP, online transaction processing. So OLTP systems, those are the engines running the daily business, right? Think about the database behind an e-commerce website. It's all about handling lots of short, fast transactions, placing an order, updating inventory, super fast, reflecting right now.
Right, needs to be instant.
Exactly. Now, OLAP systems, which is what a data warehouse is, they're designed for the total opposite. They're optimized for reading huge amounts of historical data for complex queries that slice and dice that data in different ways. Imagine asking your live e-commerce site, show me total sales by product category for every region over the last 5 years.
Oh yeah, I can see that grind things to a halt pretty quickly.
It absolutely would. The data warehouse isolates those heavy analytical jobs. It protects the day-to-day operations, keeps the business running smoothly. It's kind of like having a dedicated research library completely separate from the busy front office. Different tools for different jobs.
Okay, that makes a lot of sense. That separation is key. And I bet that idea connects back to the foundational principles from people like Bill Inmon, the father of data warehousing, right? What were his big ideas?
Spot on. Inmon's 4 characteristics, they aren't just features, they're like the design philosophy that really explains why you need that OLAP-OLTP separation. First, he said, a data warehouse is subject-oriented. So data is organized around core business concepts. Think customer, product, sales, not around the operational processes like order entry or shipping. This lines up directly with the questions the business actually wants to ask.
Okay, so focused on the what, not the how.
Precisely. Second, it's integrated. This is huge. Data comes from all these different systems, right? Each with its own naming conventions, its own codes, maybe different currencies. Integration means cleaning all that up, conforming it, standardizing it. So custod in one system and customer ID in another. They become the same thing in the warehouse, USD and euros. Standardized. This is how you actually break down those silos and get one consistent view.
Oh, I remember dealing with that early in my career, trying to match sales data from 3 systems where customer meant something slightly different in each. It was a nightmare. That integrated part sounds like a lifesaver.
It really is. Third characteristic, time variant. Unlike your operational systems that mostly care about what's happening right now, the data warehouse is all about history. It's designed to store data over long periods, years, even decades. And every piece of data is tied to a specific point in time. You absolutely need this for looking at trends, spotting patterns, doing any kind of forecasting. You have to see how things changed over time.
Makes sense. You can't forecast without history.
Right. And finally, it's non-volatile. Once data lands in the warehouse, it basically stays there. It's immutable. You don't update or delete records in the traditional sense. You typically just add new data reflecting changes. This means the data is stable. It's a permanent historical record. If you run a sales report today and run the exact same report tomorrow, you should get the exact same results for that historical period. It builds trust. It allows for auditing. It ensures decisions are based on a verifiable history.
Okay, so subject-oriented, integrated, time-variant, non-volatile. Those four pillars really create that foundation for reliable analysis separate from the daily chaos.
Exactly. They collectively drive that need for separation and define what makes a data warehouse a true analytical powerhouse.
So we had this solid blueprint, thanks to Inmon and others, a strong foundation. But then the world changed, right? We moved from these big, expensive boxes in the basement on-premise data centers to the cloud. How did that foundation adapt? Did it crumble or did it get like a superpowered upgrade?
Oh, it was a profound shift, a total upgrade. Those traditional on-premise warehouses, they were powerful for their time, but yeah, expensive, really rigid. Scaling them was a major headache. You needed huge upfront investments in hardware, software licenses, and if you needed more power or storage, that meant long waits for new servers to arrive. Plus, they were often updated in batches, maybe overnight, which wasn't great for near real-time insights.
Right, the whole procurement cycle nightmare.
Exactly. The cloud completely flipped the script. You've got data warehouses offered as services passe from AWS, Google Cloud, Azure, and the biggest game changer, probably the decoupling of storage and compute. Think about that. The place where your data lives is separate from the engines that run your queries.
Okay, so what does that actually mean in practice?
It means you can scale them independently.
Right.
Need to store way more data? Fine, scale up storage. Need more query power for a busy month end? Temporarily scale up compute. You only pay for what you use when you use it. It's elastic.
Wow, okay. That's not just a technical detail. That sounds like it completely changes the economics and the speed at which businesses can move. No more guessing capacity, years in advance, and spending millions up front.
Precisely. The cost efficiency and agility gains are massive. And these cloud platforms brought other cool tech, too, like massively parallel processing, MPP, splitting queries across hundreds or thousands of nodes working together. Super fast. And many use columnar data stores. Instead of storing data row by row like a spreadsheet, they store it column by column. This is way faster for analytical queries because those queries usually only need a few columns, not the whole row.
So you're reading less data overall for the same result.
Exactly. The whole cloud shift just democratized powerful analytics. Suddenly, analyzing petabytes of data wasn't just for the giant corporations with massive budgets.
That's a huge shift.
Okay.
Okay, so we get the what and the why and how the cloud revolutionized things. Let's talk how. Building one of these still sounds like a pretty big project. What's the typical process, the lifecycle look like, and are there different philosophies guiding the actual design?
It's definitely a structured process, or at least it should be. It kicks off with requirement gathering and planning. This is super important. You need to know what the business actually needs, what questions are they trying to answer, what KPIs matter. This means talking to stakeholders, lots of talking.
Asking what keeps you up at night, basically.
Kind of, yeah. What decisions could you make better with data? Then you move into architecture and data modeling, designing the tech stack, the schemas, how the data will actually be structured. After that, it's data integration development. This is where you build the pipelines, the ETL or ELT processes to get the data in, extracting, transforming, loading. Then comes testing and validation. You absolutely cannot skip this. Testing the integration, checking data quality, making sure queries run fast enough, and crucially, user acceptance testing or UAT. Do the business users agree that this actually solves their problem?
Right, does it work for them?
Exactly. And finally, deployment and maintenance. Go live, training people how to use it, and then the ongoing monitoring, tuning, and optimizing because things always change.
It's a whole life cycle. And within that architecture and data modeling phase, I know there's been this historical debate, almost like rival camps, Inmon versus Kimball. What's the difference there, and does it still matter today?
Yes, the classic debate. It has softened a bit now, but understanding the core ideas is still really useful. So Inmon's approach is often called top-down. The idea is you build the big, centralized, highly normalized enterprise data warehouse first. Usually in what's called third normal form, very structured, minimal data redundancy. This is meant to be the ultimate single source of truth at the most detailed level. Then, from that central warehouse, you create smaller departmental data marts for specific teams.
Okay, build a perfect foundation first, then build rooms on top. What's the downside?
The strength is massive consistency across the enterprise. The drawback: it takes a long time and a huge upfront effort before anyone in the business sees any value. Time to value can be very slow. Kimball's approach is the opposite, bottom up. It focuses on delivering value faster. You build focused, dimensional data marts, usually using those star schemas we'll talk about, for specific business processes like sales or marketing first. The key is using shared, consistent dimensions called conformed dimensions across these marts, so theoretically they can be integrated later.
So faster wins, faster ROI.
Potentially, yes. Faster time to value. The risk, if you're not careful with those conformed dimensions and the overall plan, you can end up building a bunch of disconnected silos. Accidental complexity.
So who wins, Inmon or Kimball?
Well, today, the reality is usually a hybrid approach. The strict separation isn't as common. Best practice now often involves building a stable, auditable integration layer. First, maybe using something like Data Vault, which we'll get to as that enterprise foundation. And then, from that layer, you create Kimball-style dimensional models, like star schemas. For the presentation layer, the part users actually query with BI tools. It tries to get the best of both: the consistency and auditability of a central layer, plus the speed and usability of dimensional marts.
Okay, a pragmatic compromise.
Yeah.
Makes sense. So beyond those big methodologies, what are some essential best practices you need to follow when building a modern data warehouse?
Absolutely critical ones. First, data governance and quality. A warehouse is useless, maybe even dangerous, if the data inside is garbage or misused. You need clear policies for data security, who can access what, how long data is kept, compliance with rules like GDPR or APA, and often something called master data management, or MDM, to make sure core things like customer or product are defined consistently everywhere.
Right, quality in, quality out. What else?
Second, scalable and performant design. You have to build it thinking about the future. Choose a cloud platform that can grow with you. Use smart design techniques like partitioning large tables, creating indexes for faster lookups, maybe using materialized views for common complex queries. Don't build something that hits a wall in 6 months.
Future-proofing it. Got it.
Third, comprehensive security. These warehouses hold incredibly valuable, often sensitive data. They're prime targets, so multiple layers of defense are crucial. Encryption both for data sitting there and data moving around. Multi-factor authentication for access. Fine-grained access controls, who sees what row, what column. Regular security audits, it's non-negotiable. And finally, I'd say agile development. The old way of building software, the waterfall method, where you define everything upfront and deliver it a year later, just doesn't work well for data warehousing anymore. Business needs change too fast. Using agile approaches like Scrum or Kanban, working in shorter sprints, getting constant feedback from business users, delivering value iteratively, it just leads to better outcomes and ensures the warehouse actually stays relevant.
Those all sound incredibly important. Okay, let's zoom in on the data modeling part again. You mentioned star schemas and dimensional modeling. Can you unpack those a bit more? How does that actually structure the data for analysis?
Right, so dimensional modeling, really championed by Ralph Kimball, is probably the most common structure you'll find in the part of the warehouse. Users interact with that presentation layer. The whole goal is to make the data easy to understand and query really fast, even if it means intentionally adding some redundancy. The most common form is the star schema.
Why star? Does it actually look like one?
Yeah, it kind of does. Imagine a central point with lines radiating outwards. At the center, you have your fact table. This table holds the core measurements, the numbers, the metrics from a business process. Things like sales amount, quantity sold, profit. Each row in the fact table represents a specific event or snapshot at a certain level of detail, its granularity. For example, maybe one row for each line item on an invoice, and it contains foreign keys that link out to the dimension tables.
Okay, facts are the numbers. What are the points of the star?
Those are the dimension tables. They provide all the context around the facts, the who, what, where, when, why behind those numbers. So you'd have dimensions for customer, product, date, store, maybe salesperson. These tables are usually wide, meaning they have lots of descriptive attributes like customer name, customer city, product category, store manager name. They use a special system-generated key called a surrogate key as their primary identifier. And crucially, they are often denormalized. For instance, a product dimension might have the product name, its subcategory, and its main category all in the same table, even though that repeats information. Why? To avoid extra table joins during queries.
So the fact table tells you how much was sold, and the dimension tables tell you everything about who bought it, what they bought, where and when. I can see how that structure would make querying simpler, fewer joins, like you said.
Exactly, that's the main strength. Fast query performance because of fewer joins. It's also generally simpler for business users to understand and navigate with BI tools. Drag and drop sales amount and product category, and it just works.
Okay, sounds great. But you mentioned intentional redundancy. Does that cause issues like more storage needed or risks if data needs updating? What are the downsides?
That's the trade-off, exactly. Yes, there's data redundancy, which means you need more storage space. And it can introduce data integrity risks. If a product category name changes, you theoretically have to update it in potentially thousands of rows in the product dimension. This needs careful management through your ETL process. It can also be a bit less flexible if you have really complex or rapidly changing hierarchies within your dimensions.
So the star schema is great for speed and simplicity, especially for users, but maybe not ideal for every single situation, particularly complex relationships or minimizing redundancy. What else is there?
Well, one variation is the Snowflake schema. It's basically a star schema where the dimensions themselves have been normalized.
Normalized, meaning broken down further.
Yeah. So instead of having product subcategory and category all in one dim product table, you might have dim product linking to dim subcategory, which links to dim category. It looks more like a snowflake than a simple star because the dimensions branch out.
Okay, so that reduces redundancy, I guess.
It does. Less redundancy, potentially smaller storage footprint for the dimensions. But the cost is slower query performance because now you need more joins to bring all that context back together. And it can be more complex for users to navigate. It's less common for the main presentation layer these days because the performance hit is often significant.
Got it. So star for performance, Snowflake for normalization, but maybe slower. What about that other approach you mentioned, Data Vault? Where does that fit in? Is it another alternative to star Snowflake?
Data Vault, specifically Data Vault 2.0, is a bit different. It's not primarily focused on the presentation layer that users query. It's a modeling technique designed for the integration layer of the data warehouse, that stable foundational layer we talked about in the hybrid approach. Its main goals are auditability, scalability, and flexibility, especially when dealing with lots of changing source systems. It's really built for agility.
Okay, integration layer, not presentation. What's the core idea behind it?
A key philosophy is separating the act of loading the raw data from applying business rules. Data Vault aims to ingest data exactly as it comes from the source systems, including all history, creating a fully auditable trail. Think of it like a detailed ledger. Business rules, transformations, calculations, those are applied later, downstream, when you're preparing data for specific reports or analyses, often when building those star schemas. This separation makes it incredibly robust against source system changes and provides that complete audit history.
That sounds powerful for traceability and handling change.
Yeah.
How is it structured? What are the building blocks?
It has three main components. First, hubs. Hubs represent your core business entities: customer, product, store. They are really simple, basically just containing the natural business key, like customer ID, and a unique system-generated hash key, plus some metadata. They are the stable anchors. Second, links. Links represent the relationships or transactions between hubs. So, a purchase link might connect a customer hub and a product hub. They model potentially complex many-to-many relationships without needing to change the structure of the hubs themselves. And third, satellites. Satellites hold all the descriptive attributes about a hub or a link, and crucially, they track all historical changes to those attributes. If a customer's address changes, you don't update the old record, you add a new row to the customer address satellite with the new address and a timestamp. They are append only.
Append only, so you keep every version of the truth over time.
It's exactly. Full history. And the agility comes from this structure. Say a source system changes how it stores addresses. You don't touch the customer hub. You might create a new satellite table to hold the new address format, attaching it to the same hub. The change is isolated, minimizing impact on the rest of the model.
That's clever. So if it's the integration layer, how does it relate to the star schemas people actually use for BI?
It serves as the robust, auditable foundation. You build your data vault, sometimes called the raw vault or business vault, and then you build your Kimball-style star schemas, the presentation layer or gold layer, by querying and transforming data from the data vault. So you get the best of both worlds. The historical integrity and flexibility of Data Vault in the middle, feeding the user-friendly, high-performance star schemas that the business interacts with. It's a very common pattern in modern architectures, especially in lathouses.
Right, different layers optimized for different jobs.
Yeah.
Okay, let's shift gears slightly. Getting the data into these warehouses. We hear ETL and ELT thrown around a lot. What's the deal there? Has there been a shift?
Oh, absolutely a huge shift. For years, the standard was ETL. Extract and transform load. You'd pull data from your source systems, extract, move it to a separate intermediate server where you'd clean it, reshape it, apply business rules, transform, and then you'd load the final processed data into the data warehouse, load.
Why the separate server for transforming?
Because traditional on-premise data warehouses had limited and expensive compute power. You didn't want to bog down your expensive warehouse doing all the heavy lifting transformation work. It was more efficient to do it beforehand on cheaper hardware. But the cloud changed the economics, remember. Suddenly, compute power inside the warehouse became relatively cheap, scalable, and powerful. So the paradigm flipped to ELT, extract, load, transform.
Okay, so extract the data, load it straight into the warehouse raw, and then transform it using the warehouse's own power.
Exactly. You leverage the massively parallel processing power of the cloud data warehouse itself to do the transformations after the data has landed.
And why is ELT generally preferred now?
Several reasons. Speed. Raw data is available in the warehouse much faster. Flexibility. You keep the raw data, so if you need to transform it differently later for a new use case, you don't have to go back and re-extract it from the source. You just transform the raw data again inside the warehouse. Scalability. It uses the warehouse's scalable engine. Simplicity. Often simplifies the overall data pipeline architecture.
Makes sense. Are there still times when traditional ETL is better?
Yeah, definitely. Sometimes for strict data privacy or security, you might need to mask or anonymize sensitive data before it even lands in the warehouse, so you transform first. Also, if you have incredibly complex transformations that require specialized tools or libraries not easily available inside the warehouse, doing it on a separate ETL server might still make sense, or sometimes just integrating with very old legacy systems. But generally, ELT is the dominant pattern today.
Good to know the trade-offs. What kind of tools are people using for these ELT and sometimes ETL pipelines?
It's a busy space. You've got managed ELT services like Fivetran or Stitch that are great for automating the E&L parts with lots of pre-built connectors. Just point and shoot, basically. Then there are more comprehensive platforms like Talend or Informatica that handle complex ETL, ELT, data quality, governance, the whole nine yards. They've adapted to the cloud era, too. Each cloud provider also has its own native services like AWS Glue, Google Cloud Dataflow, Azure Data Factory. These are often serverless and integrate tightly with their respective ecosystems. And for real-time data streaming into the warehouse, tools like Apache Kafka are very common.
Quite a few options there. Okay, that leads us nicely to the big platforms themselves. The cloud data warehouses, you mentioned AWS, Google, Azure, Snowflake too. Can you give us a quick comparison? What makes each one stand out?
Sure. It's important to remember the choice is really strategic. It often depends heavily on your organization's existing cloud footprint, skills, and specific needs. But let's touch on the big ones. Snowflake. Their big innovation was really separating storage, compute, and services completely. They run on AWS, Azure, or GCP, true multi-cloud portability. Key features are those independent virtual warehouses for compute that you can spin up and down, resize instantly. Zero-copy cloning is amazing for creating instant dev test environments, and things like time travel for accessing historical data easily. They're often praised for ease of use and flexibility, especially in multi-cloud setups. We saw VideoAmp get huge cost and performance gains with them.
Okay, flexibility and multi-cloud focus for Snowflake. What about Google?
Google BigQuery. It's fully managed and serverless. That's a big differentiator. You don't manage clusters or nodes. It just scales automatically behind the scenes based on your queries. It leverages Google's massive infrastructure and has deep integration with Google Cloud Services. A unique aspect is BigQuery ML for building machine learning models directly using SQL inside the warehouse. And they're adding more AI features, like using Gemini for natural language queries. Ideal if you're heavily invested in GCP or want that zero-ops serverless experience. Think Home Depot managing petabytes seamlessly.
Serverless and AML integration for BigQuery. Then Amazon.
Amazon Redshift. This is AWS's offering, built on a more traditional MPP columnar architecture, though it's evolved a lot. Its main strength is its incredibly deep integration with the entire AWS ecosystem. Features like Redshift Spectrum let you query data directly in Amazon S3 storage without loading it first. They also have hardware accelerators like AQUA. It's a very powerful option, especially if you're already an AWS shop and need high performance for complex SQL. EOS Group used it effectively for cost savings and PII protection.
Deep AWS integration and performance for Redshift. And Microsoft's Azure.
Azure Synapse Analytics. Microsoft's play here is a unified analytics platform. Synapse Studio tries to bring data integration, data warehousing, SQL pools, big data processing, Spark pools, and even connections to Power BI, all into one interface. It offers flexibility in compute. You can choose dedicated provisioned resources or serverless on-demand SQL. And of course, it has very tight integration with the Microsoft ecosystem, Azure Data Lake, Azure ML, Power BI. Great choice if you're a Microsoft-centric organization looking for that end-to-end experience.
Unified platform and Microsoft integration for Synapse. It really seems like the best choice depends heavily on your context, your existing cloud, your team's skills.
Exactly. There's no single best platform. It's about strategic fit.
So looking ahead now, we've covered a lot of ground. What's the big picture trend? Where is data warehousing heading? And what are the key takeaways for listeners trying to make sense of all this?
The biggest trend, the one everyone's talking about, is the data lakehouse. It's really this convergence, this merging of the data warehouse and the data lake.
Lakehouse, bringing the lake and the house together. What's the point?
Pretty much. Historically, you had your data warehouse for structured data for BI and reporting, and you had your data lake for raw, unstructured, semi-structured data, often used for data science and machine learning. Two separate systems, two silos. The lakehouse aims to break down that wall, create a single platform, a single architecture that can handle both traditional BI workloads and advanced AML workloads directly on the same data, often stored in open formats in the lake. It's about unifying analytics and AI, moving from just reporting on the past to predicting and shaping the future all in one place.
That sounds like a really powerful vision, unifying everything. So, based on everything we've discussed, what are your main pieces of advice, your key recommendations for our listeners?
Okay, 4 key things to keep in mind. First, start with the business why, always. Don't get seduced by cool tech. Define your clear, measurable business objectives first. What decisions need support? What outcomes are you aiming for? Let that drive your technical choices.
Always start with the problem you're solving. Got it.
Second, embrace a hybrid modeling strategy. Don't get stuck in the old Inmon versus Kimball religious wars. The modern best practice is often layered. Use something robust and auditable like Data Vault for your core integration layer, and then build user-friendly performance star schemas on top for reporting and BI. Get the best of both.
Right, layered approach. Makes sense.
Third, choose your platform based on strategic fit, not just features. Don't just pick the shiniest object. Think about your existing cloud strategy, if any. Your team skills, what do they know? How much operational management do you want to handle? Serverless versus provisioned? Do you need multi-cloud? Make a strategic choice that aligns with your broader goals.
Think long-term and holistically.
Yeah.
Good advice.
And finally, plan for a unified future. Even if you're just building a traditional data warehouse today, design your architecture with the data lakehouse concept in mind. Think about how you might incorporate unstructured data later, how you can enable AML workloads alongside BI. Build with that convergence in mind so you're ready for what's next.
Fantastic advice. Wow, what an incredible journey we've taken today. From understanding the core purpose, that single source of truth, and the foundational characteristics of a data warehouse, through its evolution into the cloud, the different ways to structure and model the data like stars and vaults, the shift from ETL to ELT, and finally navigating the landscape of powerful cloud platforms. It's so clear this isn't just some niche technical topic. Data warehousing is really fundamental to how organizations make smarter, faster, more strategic decisions today.
Absolutely. And maybe the most exciting thing to think about connecting it all isn't just how these systems help us understand the past better through reporting, it's how they're evolving to help us actively shape the future. When you truly integrate BI and AML on a unified platform like the Lakehouse, think about the possibilities. What completely new insights could you uncover? What processes could you automate? When historical analysis flows seamlessly into predictive modeling, that ability is going to transform practically every industry. What will you unlock when your data foundation becomes truly unified and intelligent? Something to think about.